Okay, so while we're out for this little surprise break because of COVID, um, I'm going to post some additional notes and such. Mostly, this will serve as review, or just some of you would probably benefit from seeing some of this in another format. Um, this also, for those of you who are out, will kind of give you another run through of what we're doing before hopefully we're all back in a week. This will not perfectly match what we were doing in class. Same information, different order because this is out of an older textbook. But it's still the same information. So, for instance, in this set of notes, in this textbook, we did the graphing before we did the scientific notation and dimensional analysis. So I'll just go through that here and we'll run from there. So we've talked about in class, we'll talk about it again here, the different types of graphs. So a bar graph, we show how many of something are in each category. So we're comparing numbers and categories. So here, for instance, number of students with each grade across a test. And this is probably about how mine will run. We've got that typical bell curve, which is used in psychology to explain a lot of things. Pie graph shows the whole broken down into its parts. So here, the percentage of students in each grade at some random high school. Or a line graph shows continuous change, really is. You can call it change over time. Doesn't always require time. So here we have, cost of tickets across who knows how many years, but you can see the change. Now, in chemistry, we will, I hesitate to say always, but almost always use a line graph. Because most of the time what we're doing is we're comparing our independent and our dependent variable to see what the differences are. So to have a good line graph, really to have a good graph at all, I have to have my axes labeled with units. Okay, I have to have a title. I need to use all of the available space. And it needs to be neat. Okay, if I can't read it, it's not really doing me a whole lot of good. So the next thing we're going to look at is scientific notation. And we did a good bit of this, a little bit of this in class. Now, we use scientific notation, it says here again, for very large or very small numbers. And sometimes that's what we use to indicate precision, because sometimes when we need to round to a certain number of sig figs, the only way to do that in an accurate way or in a concise way is to put it in scientific notation. So, scientific notation is a number between 1 and 10 times 10 to some exponent. So, for example, 800, I could break that down, okay? And what this is showing you is that 800 is 8 times 10 times 10. So that's 8 times 10 to the second, okay? That's what scientific notation means. So 0.0014 means 1.4 divided by 10 divided by 10 divided by 10. That's where we get the negative exponent at the end of it. So, a couple of examples. I'm going to put some in scientific notation. I'm going to take some out. Okay, if I'm putting this in standard form, then I'm moving my decimal this many places. So it was 1.7 times 10 to the negative 5, which means it was a number that was less than 1. So I'm moving my decimal this way, 1, 2, 3, 4, 5 places. So I'm going to have 0.0000187. If it's a positive exponent, then that means my number was greater than 1, so I'm moving my exponent this way 8 places. So 1, 2, 3, 4, 5, 6, 7, 8, basically. I don't know if I put enough lumps in that or not. So 3, 7, 0, 0, 0, 0, 0, 0, 0. Because that would give me 3, 6, 7, 8 places if I moved all of that out. 7.88 times 10 to the first. So we only moved the decimal 1 place here. So to take it out of scientific notation, it's going to be 78.8. 2.164 times 10 to the negative 2. We moved the decimal 2 places. So I have 0.02164. Okay, that negative exponent means I had a number less than 1. It doesn't mean I had a negative number. Now this next set I need to put into scientific notation. Okay, so we're putting these into scientific notation. So I'm going to take my decimal here is at the end of the number. So I'm going to move my decimal until there's only one thing in front of it. So 1.234 times 10 to the, well, how far do I have to move it? 1, 2, 3, 4 places. Here I have 0.369. I need one thing in front of the decimal. So 3.69 times 10 to the negative 1 because I moved my decimal to the right. 1, 2, 3 places. So 8 times 10 to the negative 3. Here I'm moving it 1, 2, 3, 4, 5, 6, 7. So that I have one thing in front. So 1 times 10 to the 7th. Okay. Some of you, I'm not sure how you're coming up with your exponent. Because you'll move the decimal, for instance, here. I'll change color so you can see where I'm writing. And then your exponent is something severely different than what it needed to be. So we're going to have to figure that out over the next little bit. Now, the next chunk of this, we're looking at doing the math and carrying the units with it. Remember, I talked about in chemistry, we have a number and a unit. 99.99% of the time, you will have at least that. Usually a number, a unit, and a substance. And you do the same math with the unit that you did with the number. So if this is the math that I'm doing, when I plug all of that in the calculator, we get 0.64, and I have to do the same math with my units. So I have kilograms, meters over seconds squared, because I had seconds and seconds at the bottom. Okay, here I have grams, seconds, seconds. Now, one of these is going to cancel out. So when I feed the calculator, I get 0.17. I didn't write that very well. Let me clean that up a little bit. .17. My units is going to be grams per second. Okay. I'm going to scroll a little bit. I'm going to skip this. Why that stayed there, I don't know.